The universe is actively writing its own future. We will explore 25 cosmic events with the power to reshape all of existence. This journey reveals how the dramatic transformation of stars and the gradual evolution of space-time influence the fate of galaxies and the potential for life. You will gain a new perspective on the forces that will define reality for eons to come. What happens when a star encounters a black hole? And could a single quantum event rewrite the laws of physics? This exploration challenges everything we know about our place in the cosmos. Which cosmic event do you think holds the most profound consequence for our future? The universe's story may ultimately be one of increasing quiet. This first cosmic event, often called the heat death, presents a future defined not by a bang but by a slow, steady fade. It is a consequence of a fundamental cosmic rule, entropy, which in simple terms is the natural progression from order to disorder. Theoretical physicist Sean Carroll explains how the arrow of time itself is tied to this increasing entropy, a one-way street leading toward a state of perfect balance. As dark energy continues to push the cosmos apart, galaxies will vanish over the cosmic horizon, their light never to reach us again. The formation of new stars will cease entirely, and the existing ones will, one by one, exhaust their fuel and fade from view. Over almost unimaginable eons, even the most stable structures, like black holes, are predicted to slowly dissipate through a quantum process. What remains is a universe grown cold and dark, a thin, uniform sea of isolated particles and radiation where no energy differences exist to power any process or any thought. How does the inevitability of such a quiet, final balance shape our understanding of purpose in a cosmos that seems to be winding down? This distant possibility underscores the fleeting brilliance of the cosmic structures we see today, making the intense and immediate events we will explore next seem all the more striking by contrast. But the cosmos holds other, far more dramatic conclusions. This second event, known as the Big Rip, presents a future not of a quiet fade but of a profound transformation. In this scenario, the mysterious force we call dark energy does not merely accelerate the universe's expansion, it grows infinitely stronger. Eventually, its repulsive power would overcome every force that holds reality together, from the gravity binding galaxies to the forces inside a single atom. Cosmologist Robert Caldwell has explored models where a specific form of this energy, termed phantom energy, leads to a finite time singularity, a definitive moment when everything is fundamentally changed. The transition would unfold in a distinct sequence. First, the immense clusters of galaxies would be gently separated. Then, individual galaxies like our own Milky Way would drift from their neighbors in a quiet, steady movement. Next, stars would be drawn from their galaxies, and planetary systems would journey into the vast expanse. Finally, in a last, brief moment, planets, stars, and even the atoms that compose all matter would be separated into their most basic components. The timeline for such an event is uncertain, hinging on the precise nature of dark energy, with some estimates placing it billions of years from now. What would it mean for life if the very fabric of space-time, the stage upon which existence plays out, is not a permanent foundation but a temporary structure? This dramatic possibility stands in clear contrast to the slow fade of heat death, revealing a cosmos where the ultimate influence may lie not in gravity or matter, but in the space between them. Yet the very laws of physics that govern our reality might not be as permanent as they seem. This third cosmic event, known as vacuum decay, presents a shift not from a colossal collision or a slow fade. but from a subtle instability woven into the fabric of space itself. It begins with a single, random quantum event, a tiny bubble of what physicists call a true vacuum forming somewhere in the cosmos. This bubble would not be empty, but filled with a new, lower energy state of reality. Its properties would be guided by entirely different fundamental constants and forces. The moment this bubble appears, it would begin expanding in all directions at the speed of light, a wall of fundamental change rewriting the universe as it travels. Inside this growing sphere, the laws of physics as we know them would no longer apply. The forces that bind atoms together, that allow for stars and planets and life, would be permanently transformed. This transition would likely make the formation of complex matter, and therefore life, no longer possible. There would be no warning, no way to see it coming, as the bubble's frontier moves at the ultimate speed limit, the speed of light itself. Once begun, this process would be completely unstoppable, replacing everything in its path without leaving a trace. How can we reconcile our perception of a stable, predictable cosmos with the thought that its entire rulebook could be instantly rewritten by a single, random quantum fluctuation? This idea, explored by thinkers like Stephen Hawking, suggests that our universe might not be in its most stable configuration, but is merely resting in a temporary state, a false vacuum, waiting for a trigger to settle into its true, and for us, profoundly different form. This deep fragility shifts our gaze from the large-scale fate of galaxies to the very bedrock of existence, prompting a look at other transformations that could reshape the cosmos from the ground up. Our own galaxy is not an island in a static sea, but a ship on a collision course. In approximately 4 billion years, the Milky Way and its colossal neighbor, the Andromeda galaxy, will begin a gravitational dance that will reshape our local universe. This merger is not a matter of chance, but an unavoidable destiny driven by the mutual pull of gravity between these two titans. Data from the Hubble Space Telescope has removed any lingering doubt, confirming their trajectory and bringing the future of our galactic home into sharp focus. The process will unfold over billions of years, a slow-motion ballet where the two galaxies will first swing past each other, their gravitational forces twisting and stretching their spiral arms into long, streaming tails of stars and gas. They will then swing back, passing through one another again and again before finally settling into a single, new galaxy, likely a large, featureless elliptical shape. The vast emptiness of space means that while entire galaxies are interacting, the stars within them are so far apart that direct encounters between them are extraordinarily rare. The real drama will unfold in the colossal clouds of gas and dust. As these clouds are drawn together by the galactic interaction, they will compress, triggering powerful waves of new star formation. Brilliant blue clusters of young stars will ignite, lighting up the merging galaxy with stellar nurseries. For any future observers within our solar system, the night sky would transform into a breathtaking spectacle. The familiar band of the Milky Way would be gone, replaced by a luminous, glowing tapestry of scattered stars and shining gas clouds. The gravitational turbulence could send our solar system into a new, distant orbit around the galactic core, or there is a small chance it could be set adrift, journeying into the vast expanse of intergalactic space. This monumental reshuffling of cosmic real estate demonstrates that even the largest structures in the universe are in constant flux, setting the stage for transformations on a much more personal, stellar scale. Such a stellar explosion, happening a mere stone's throw away in cosmic terms, would be far more than a spectacular light show. A supernova is the powerful final chapter in the life of a massive star. An event that unleashes in a single burst more energy than our Sun will produce over its entire multi-billion-year life. If one were to occur within about 100 light-years of Earth, the consequences would be profound, a mix of creative and destructive forces on a planetary scale. Historically, we have seen distant cousins of such an event. The supernova that created the beautiful Crab Nebula was recorded by astronomers in the year 1054, visible in the daytime sky for nearly a month. These cosmic explosions are the universe's primary forges for heavy elements, scattering the iron in our blood and the calcium in our bones across interstellar space, seeding future generations of stars and planets. Yet, up close, the same process that gives us these essential materials could also pose a significant challenge. A nearby supernova would bathe our planet in intense radiation, from ultraviolet light to a torrent of high-energy cosmic rays. This radiation could affect Earth's protective ozone layer, potentially triggering shifts in climate and influencing life on the surface. Our modern technological society would be particularly vulnerable, with the deluge of particles posing a risk to satellite communications, power grids, and delicate electronics on a global scale. Consider the star Betelgeuse, a red giant in the constellation Orion that is nearing the end of its life. When it does go supernova, it will shine as brightly as a full moon in our night sky, visible even during the day for weeks. While it is safely distant at over 600 light-years, its brilliant transformation serves as a constant reminder of the dynamic and sometimes volatile nature of our galactic neighborhood. The aftermath of such an event leaves behind an incredibly dense remnant, either a rapidly spinning neutron star or, for the most massive stars, the formation of a new black hole. How would human civilization, with all its scientific understanding, process the sudden, undeniable proof of a star's final act occurring in our celestial backyard? The cultural, philosophical, and scientific reflections would ripple across the globe, forever changing our relationship with the cosmos. This dramatic stellar transition, while a potential hazard, is also a vital part of the cosmic recycling process, creating the very conditions for new possibilities, including some of the universe's most enigmatic objects. That same process which forges new black holes can also unleash a far more focused and potent form of energy. Gamma-ray bursts are the universe's most powerful lighthouses, projecting narrow beams of intense radiation born from the transformation of a massive star or the merging of two neutron stars. If such a beam were ever to sweep across Earth, it would deliver in mere seconds more energy than our Sun will emit across its entire 10-billion-year lifetime. This is not a broad, expanding sphere of energy like a supernova, but a precise, relativistic spear aimed by chance directly at our planet. Satellites like Swift and Fermi have observed these events for years, their detectors lighting up with signals from galaxies billions of light-years away, a testament to their staggering power. Most originate from far beyond our Milky Way, their energy softened by cosmic distances, but a burst within our own galaxy and pointed our way presents a clear and present question for our world. The immediate effect would be a profound alteration of our atmosphere. The intense radiation would break apart nitrogen and oxygen molecules, triggering a chemical cascade that transforms the planet's protective ozone layer. Without this shield, the surface would be exposed to elevated levels of ultraviolet radiation from our own sun. The resulting environmental shift could influence the base of the food chain, like phytoplankton in the oceans, and contribute to long-term climate changes. The truly thought-provoking aspect is the randomness of it all. A star transforms in a distant spiral arm, its final moments producing jets of energy that just happen to be aligned with our tiny, pale blue dot. There is no warning, no way to predict the alignment of that cosmic event. What preparations could humanity possibly develop against an unseen phenomenon that travels at the speed of light, offering no time for reaction or response. This possibility invites a humbling recognition of our biosphere's delicate nature, a gentle bubble of life existing in a cosmos capable of immense and distant releases of energy. The study of the lingering afterglow from these bursts provides crucial clues into the extreme physics of stellar transformation and the formation of the very relativistic jets that might one day influence our own story, linking these fleeting flashes directly to the emergence of the universe's most mysterious objects. At the heart of a supernova's brilliant transformation lies an even more profound creation. The formation of a stellar mass black hole begins when a giant star, many times heavier than our Sun, finally burns through the last of its nuclear fuel. With no outward pressure from fusion to hold it up, the star's own immense gravity wins a final, decisive victory. The core collapses in upon itself in a matter of seconds, compressing a mass greater than our Sun into a point of incredible density, a singularity. This process, which often powers the supernova explosion that sends the star's outer layers streaming into space, leaves behind a region of space-time so deeply curved that not even light can escape its pull. The boundary of this region is the event horizon, the ultimate threshold of no return. Physicists like Kip Thorne have spent decades exploring the unusual properties of these objects, which we can now detect not by seeing them directly, but by observing their profound effects on everything around them. When a black hole draws in gas from a nearby companion star, that material does not fall straight in. Instead, it spirals into a flattened, superheated whirlpool called an accretion disk, glowing intensely with X-rays and other high-energy radiation that signal the black hole's presence across the cosmos. The true revolution in our understanding came with observatories like LIGO and Virgo, which have felt the ripples in spacetime itself when two of these dark objects spiral together and merge. The energy released in such a union is staggering, vibrating the very fabric of the universe in a burst of gravitational waves. But black holes are not simply cosmic vacuum cleaners. They play a surprising role in the life cycle of galaxies, as the energy and powerful jets from their accretion disks can heat surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback mechanism helps regulate the growth of galaxies, including our own Milky Way. How do we reconcile a singularity, a point where the known laws of physics simply break down, with our quest for a complete understanding of the universe? The existence of black holes stands as a lasting invitation, a gravitational mystery written into the cosmos, pushing us to look deeper into the behavior of their even more massive and influential cousins. These supermassive black holes, millions or even billions of times the mass of our Sun, are not static anchors. They are dancers, and when their host galaxies merge, they begin a slow, gravitational spiral toward one another. Drawn together by friction with surrounding stars and gas, they form a binary pair, a cosmic partnership that tightens over millions of years. Their orbital dance sends powerful, rhythmic ripples through spacetime itself, a gravitational wave signal so immense it could, in theory, be detected across cosmic distances. This is not a quiet event. As they draw closer, their immense gravity reshapes the galactic core, sending stars into new, unpredictable paths or even guiding them outward from the galaxy on high-speed journeys into the void. The energy released in their final union is almost beyond comprehension. For a brief, dazzling moment, the merger can outshine every single star in the galaxy combined, a flash of gravitational energy that momentarily dwarfs the collective light of hundreds of billions of suns. This incredible release can have one of two dramatic consequences for the newly formed, even more massive black hole. It can receive a powerful recoil, a kick from the asymmetrical emission of gravitational waves that might propel it entirely out of the galactic center, sending it wandering through its own galaxy. Alternatively, the merger can funnel vast amounts of gas toward the new black hole, igniting a brilliant quasar, an active galactic nucleus whose intense radiation and powerful jets can heat surrounding gas clouds for thousands of light years. This heating can influence the formation of new stars for eons, effectively creating a pause in the galaxy's growth. What can these colossal, ancient events teach us about the infancy of the universe itself? Observing the gravitational waves from such mergers would offer a direct window into the dynamic early epochs when the first galaxies and their central black holes were assembling, revealing how the largest structures we see today were fundamentally shaped by these titanic encounters. The aftermath of a supermassive black hole merger is not an endpoint, but a new chapter that guides the future evolution of an entire galaxy, tying its fate into the larger, interconnected patterns of the cosmos. Deep within the heart of an ancient galaxy, a sleeping giant stirs. A supermassive black hole, having drifted through a dense reservoir of gas or encountered a wayward star, begins to draw in material. This is the ignition of a quasar, a cosmic engine of almost unimaginable power. As vast rivers of gas and dust spiral inward, they form a seething, luminous whirlpool around the black hole, an accretion disk heated to millions of degrees. The energy released is so intense that this single, relatively tiny region can outshine the collective light of every one of the galaxy's hundreds of billions of stars. Quasars are the brilliant beacons of active galactic nuclei, representing a distinct and transformative phase in a galaxy's life. They were far more common in the early universe, when galaxies were gas-rich and chaotic, and their brilliant light serves as a perfect probe. As this light travels for billions of years to reach our telescopes, it passes through clouds of hydrogen and other elements in the intergalactic medium. By analyzing the specific fingerprints left on the quasar's light, astronomers can map this cosmic web, deciphering the composition and structure of the vast emptiness between galaxies. The newly operational James Webb Space Telescope is now looking back to the universe's first billion years, spotting these brilliant objects and revealing their crucial role in a process called reionization, a pivotal era when the first light sources began to clear the cosmic fog that filled space. But the influence of a quasar is not merely a distant spectacle. The intense radiation and the pair of relativistic jets that often erupt from its poles exert a controlling influence on the entire galaxy. These powerful outflows heat the surrounding reservoirs of cold gas or even push them entirely out of the galaxy. Without this cool gas, the raw material for new star formation is removed. This process, known as feedback, acts as a cosmic regulator, effectively putting a ceiling on the galaxy's growth and influencing the final size and shape it will take. How does an object born from such profound darkness become one of the universe's most brilliant forces for creation and regulation? The awakening of a quasar demonstrates that even the most powerful engines in the cosmos can be essential architects, sculpting the evolution of their homes on a truly grand scale and linking the fate of a single black hole to the destiny of an entire island universe. Our own star, the Sun, holds a predictable yet profound destiny written in the language of nuclear fusion. In about 5 billion years, its core will exhaust the hydrogen fuel that has sustained its stable glow for so long, marking the end of its main sequence life. This is not a sudden collapse but a dramatic transformation. As fusion wanes in the core, the Sun's delicate balance will shift, and its outer layers will begin a massive expansion. It will swell into a red giant, its outer atmosphere reaching out across the inner solar system. Mercury and Venus will be engulfed and transformed, their material reclaimed by the star. Long before the Sun's surface even approaches our world, the increasing solar radiation will have rendered Earth a scorched and barren place, its oceans gone and its atmosphere carried away on the stellar wind. The Sun's core, now a dense sphere of helium and then carbon and oxygen, will continue its inward journey, no longer able to support its own weight through fusion. It will ultimately release its vast, colorful outer layers into space, creating a brief, beautiful planetary nebula that will glow for thousands of years before fading from view. All that will remain is the stellar core, compressed into an Earth-sized object of incredible density, a white dwarf. This enduring remnant, containing nearly half the Sun's original mass, will have no internal energy source, destined to slowly cool over trillions of years into a cold, dark ember. This entire process, from main sequence star to quiet remnant, is a well-understood journey mapped by our models of stellar structure. The transition of our Sun, while closing the story of our solar system, is also an act of cosmic generosity. The elements forged in its core and released into the void, the carbon and oxygen and other heavy atoms, will be scattered into the interstellar medium. There they will mix with gas and dust, becoming the raw materials for new stars, new planets, and perhaps one day, new possibilities for life. How does the ultimate fate of our own star, a personal event on a galactic timescale, reshape our understanding of legacy? It tells us that the life cycles of countless similar stars are not merely endings, but essential chapters in the universe's continuous story of building, transforming, and recycling the very stuff of existence. Even the universe's most enduring structures are not truly permanent. The evaporation of a black hole through Hawking radiation reveals a profound quantum whisper at the edge of space-time, a process that challenges the very definition of these cosmic giants. Stephen Hawking proposed a mechanism where the intense gravitational field just outside the event horizon influences the quantum foam that permeates all of space. Pairs of virtual particles, one with negative energy and one with positive, constantly flicker in and out of existence. Normally, they annihilate each other almost instantly. But at the black hole's boundary, the tremendous gravity can pull them apart. If the negative energy particle falls across the event horizon, it reduces the black hole's total mass, while its positive energy partner escapes into space as a tiny amount of radiation. This slow, steady trickle of energy escaping a black hole means these objects have a finite lifespan. For a typical stellar mass black hole, the Hawking radiation is unimaginably faint, far weaker than the cosmic microwave background glow that fills the universe. The timescale for such a black hole to evaporate is longer than the current age of the cosmos by an almost incomprehensible factor. It is a process measured in googolls of years. Yet for hypothetical, much smaller primordial black holes that might have formed in the universe's earliest moments, the story is different. Their smaller size means a stronger Hawking radiation output. If they exist, some could be reaching the end of their lives now, evaporating in a final, brilliant flash of high-energy gamma rays that our telescopes might one day detect. This elegant theory, however, leads to one of the most stubborn puzzles in modern physics, the information paradox. According to quantum mechanics, information about what falls into a black hole should never be truly lost. But if the black hole evaporates completely, radiating only a featureless thermal glow, what happens to all that detailed information about the stars, planets, and dust that formed it? Does it vanish, violating a fundamental law, or is it somehow encoded in the radiation in a way we do not yet understand? How does the introduction of a lifespan for black holes reshape our view of cosmic eternity? It suggests that even the darkest and most seemingly permanent fixtures in the cosmos are subject to the subtle, transformative laws of quantum mechanics, connecting their ultimate fate to the gradual unfolding of deep time. The silent, dark traveler moves through the void between stars, a rogue black hole drifting far from any galactic center. These solitary objects, flung from their home galaxies during ancient mergers, wander the interstellar highways, their presence revealed only by the subtle bending of starlight, an effect astronomers call microlensing. Their journey is one of profound isolation, but should one chart a course through our own solar system, its visit would be anything but quiet. The change would begin not with a collision, but with an unseen influence. Long before any telescope could observe it, the black hole's immense gravity would begin to gently pull on the outer reaches of our system, subtly shifting the delicate orbital balance that has held for billions of years. The Oort cloud, that distant shell of icy material surrounding our sun, would be stirred into motion. Many comets would be nudged from their stable paths, sent on new trajectories that curve inward toward the sun, raising the possibility of significant encounters here on Earth. As the dark traveler drew nearer, its gravitational pull would grow stronger, altering the paths of the planets themselves. Orbits could become more stretched, shifting planetary climates to new conditions, or in a more extreme situation, a planet might receive a gravitational push strong enough to send it away from the solar system entirely, beginning an endless journey into the vast dark galaxy. The black hole would not need to directly touch anything to initiate this cosmic rearrangement. Its gravity alone would be a perfectly sufficient force for transformation. How would we even know it was approaching? The first clues might be unexplained shifts in the outer solar system, slight variations in the positions of distant objects that do not match our gravitational expectations. We might witness a curious microlensing event close to home, watching as a familiar star temporarily brightens and changes shape from the black hole's lensing effect. While the chance of such a close meeting is incredibly small within any human timescale, its possibility highlights a fundamental truth about our galactic surroundings. It is not a fixed, orderly mechanism, but a dynamic and sometimes surprising expanse, where dark, massive objects journey through the cosmic depths. This idea offers a strong reason to deepen our mapping of the galaxy's unseen substance, an effort that links directly to the wider mystery of dark matter. What other unseen travelers might be moving through our neighborhood, their presence still unknown to our view? The search for these dark wanderers reminds us that our place in the cosmos, while steady for now, belongs to a much larger and more active gravitational web. The same cosmic environment that delivers the building blocks for life can also deliver its most profound challenges. A massive comet or asteroid, a remnant from the solar system's early formation, carries the potential to reshape a world in a single, fiery moment. 66 million years ago, a city-sized object struck the Earth near what is now the Yucatan Peninsula. The Chicxulub impact released energy billions of times greater than a nuclear weapon, instantly creating a crater over 100 miles wide. The immediate effects were immense, but the long-term consequences were what truly transformed the planet. Vaporized rock and immense volumes of dust were thrown high into the atmosphere, shrouding the globe in a veil that blocked sunlight for years. This impact winter halted photosynthesis, collapsing food chains and leading to the transition of an estimated 75% of all species, including the non-avian dinosaurs. This planetary scale event demonstrates how a single, random collision can act as a powerful force for evolutionary change, clearing dominant life forms and opening ecological niches for new creatures like small mammals to flourish and diversify. Today, programs like NAS, a Planetary Defense Coordination Office, diligently scan the skies, cataloging near-Earth objects to assess any future risks. Their work helps us understand the orbits of these potential impactors, giving us, for the first time in history, the potential to foresee and perhaps even alter the trajectory of a distant object. The lingering question is not if another large impact will occur, but when. How does this ever-present, low-probability event influence the long-term story of life in the cosmos? It suggests that biospheres may not evolve along a smooth, predictable path, but are periodically reset by external events, making the survival and advancement of life a fragile and precious narrative against a backdrop of cosmic randomness. This local event holds a universal implication that the quiet space between planets is not entirely empty, but filled with ancient travelers whose chance encounters can steer the destiny of worlds. What if the lights in the sky are not all natural? The 14th cosmic event is not a collision or a collapse, but a discovery, the detection of a Kardashev Type 3 civilization. This is a culture so advanced it has learned to harness the entire energy output of its home galaxy. On the scale proposed by astronomer Nikolai Kardashev, humanity remains below a Type 1, a civilization that masters its home planet's energy. A Type 3 civilization represents a stage of development almost beyond our comprehension, and its activities would paint the cosmos with observable signatures. Our telescopes might detect entire star systems consistently dimmed by vast structures like Dyson spheres, engineered to capture a star's full light. We might find galaxies where the infrared glow of waste heat outshines the combined light of all its stars, or notice patterns in stellar light that suggest artificial manipulation on an unimaginable scale. The ongoing search for extraterrestrial intelligence is actively looking for these technosignatures, scanning the heavens for any anomaly that cannot be explained by physics alone. Finding such evidence would be the single most profound discovery in human history. It would instantly answer the ancient question of whether we are alone, while simultaneously presenting a universe filled with a presence far grander than we ever envisioned. The very existence of a Type 3 civilization suggests that intelligent life can navigate the great challenges, overcoming potential hardships like resource scarcity or technological risks to achieve a longevity measured in cosmic eras. What would it mean for our own future to know that such a destiny is possible? The knowledge that another culture has successfully traversed the vast expanse of time to command the energy of stars would fundamentally reshape our own aspirations, our science, and our philosophy. It could either inspire a new age of cooperative human advancement or present a humbling perspective on our own nascent place in the galactic community. This search for cosmic company connects our deepest questions about life's purpose to the practical, ongoing analysis of starlight, reminding us that the universe's greatest transformation might not be a physical event, but an intellectual and cultural revelation. Our understanding of physics rests upon a foundation that might be temporary. The universe could be like a supercooled liquid, existing in a delicate state that a single jolt could transform. This 15th event is a phase transition of the quantum vacuum, a fundamental rewriting of reality's rules. Just as water shifts from a liquid to a solid when it freezes, the underlying fields that define our cosmos could suddenly settle into a new, more stable state. We know such shifts happened in the universe's first moments, like the electroweak transition that separated the electromagnetic and weak nuclear forces. A future transition, perhaps sparked by a rare high-energy event in space or even an experiment here on Earth, would create a bubble of this new reality. This bubble would expand at the speed of light, its boundary an unstoppable wall of change. Inside, the fundamental constants we rely on, the mass of particles, the strength of gravity, even the number of spatial dimensions, could be completely different. The laws that allow for atoms, stars, and life would be replaced by a new, unknown set of rules, Cosmologists probe this possibility by studying the Higgs field, which gives particles their mass. Current models suggest our vacuum is metastable, not perfectly stable, meaning it is a valley that is deep, but not the deepest possible one. A transition would push it into the true lowest state. There would be no warning as the wave of change moves at light speed, making the entire event completely undetectable until it was already upon us. How does the potential for our entire rulebook of physics to be instantly rendered obsolete influence the very nature of scientific inquiry? It places a profound question at the heart of our quest for knowledge, suggesting that the reality we study so carefully might be just one temporary expression of a much deeper and more fluid cosmos. This echoes the idea of vacuum decay, revealing a shared delicacy in the bedrock of existence, a theme that continues as we look toward the stars and consider the ultimate fate of their light. Two dead stars, each more massive than our Sun yet compressed into a city-sized sphere of pure nuclear matter, complete a final spiral that began millions of years ago. Their collision is a spectacle of cosmic alchemy, an event that forges the universe's most precious treasures. When the Laser Interferometer Gravitational Wave Observatory, LIGO, and its partner Virgo detected the event known as GW170817 in August 2017, they captured the first direct evidence of two neutron stars merging. The observation was a triumph of multi-messenger astronomy, as the faint ripple in spacetime was followed just seconds later by a short gamma-ray burst and then a rapidly brightening glow in visible light, a kilonova. This brilliant afterglow is the signature of rapid neutron capture process, or R-process nucleosynthesis, the mechanism that creates roughly half of all the elements in the universe heavier than iron. In the dynamic environment of the merger, neutrons are drawn from the colliding stars and packed onto atomic seeds at an incredible rate, building up nuclei of gold, platinum, uranium, and other heavy elements in a matter of seconds. The subsequent kilonova explosion then scatters these newly forged metals across interstellar space, seeding future generations of stars and planets. The gold in a wedding ring or the platinum in a catalytic converter was likely born in such a powerful, stellar encounter billions of years ago. What does this tell us about the chemical richness of our galaxy? It reveals that the very materials that make up our world and our technology are the direct result of these rare and transformative events, linking human existence to the dramatic final moments of ancient stars. The aftermath of the merger itself is a question of mass. If the combined object exceeds a critical threshold, it will immediately collapse into a black hole. If it just barely stays below that limit, it may form a hypermassive neutron star, a bizarre, rapidly spinning object that pulses with magnetic fields and vibrations, offering physicists a unique laboratory to study matter at densities impossible to create on Earth. These fleeting, brilliant encounters are not just cosmic jewelry makers. They are fundamental engines that dictate the elemental diversity of the cosmos, ensuring that the universe is not just a sea of hydrogen and helium, but a complex and chemically rich environment capable of forming planets and nurturing life. Deep within the heart of a city-sized star, a silent shift occurs. A pulsar, the universe's most precise clock, suddenly stutters. For decades, these spinning neutron stars have been celebrated for their unwavering rhythm, their lighthouse-like beams sweeping past Earth with a regularity that rivals atomic timekeeping. But occasionally, without any warning, a pulsar's spin will abruptly increase by a tiny but measurable fraction. This is a pulsar glitch, a fleeting hiccup that betrays the incredible dynamism hidden beneath a seemingly solid, ultra-dense surface. The cause is thought to lie in the star's bizarre interior. A neutron star's outer crust is a rigid lattice of atomic nuclei, but its inner core is believed to contain a superfluid, a frictionless state of matter where neutrons can flow without any resistance. As the pulsar's rotation gradually slows over time, this superfluid can spin faster than the crust. A glitch happens when this differential becomes too great, perhaps when the vortices in the superfluid suddenly unpin from the crust, or when the crust itself experiences a structural shift of planetary proportions. The result is a transfer of rotational momentum, a stellar speed-up that makes the pulsar's clock jump forward. The Vela pulsar, a well-studied celestial beacon, has exhibited this behavior multiple times, each event providing a precious data point. After the initial jump, the pulsar doesn't simply resume its old pace. It enters a period of gradual recovery, slowly relaxing back toward its pre-glitch spin rate over weeks or months. This recovery phase is just as telling as the glitch itself, offering clues about the viscosity and structure of the star's interior layers. How can an event lasting mere seconds teach us about matter compressed to densities far beyond anything we can create on Earth? Each glitch is like a brief ultrasound of a neutron star, allowing physicists to peer into an environment where the rules of quantum mechanics manifest on a macroscopic scale. This subtle stellar phenomenon transforms these distant objects into unparalleled cosmic laboratories, testing our models of how matter behaves when pushed to its absolute limit. The precise ticking of a pulsar is not just a cosmic convenience, but a delicate signal masking a world of profound and active transformation, a reminder that even the most stable appearing objects in the universe hold dynamic secrets within. Our solar system's journey is not through an empty void, but a dynamic sea of gas and dust. Every few million years, this path leads us directly into a dense molecular cloud, a cold, dark nebula where the raw material for new stars resides. This encounter would trigger a profound change in our first line of defense, the heliosphere. This vast bubble, created by the sun's constant outflow of charged particles, envelops all the planets and shields us from the intense galactic cosmic rays that stream through the galaxy. As we move into the cloud, the external pressure from the dense interstellar material would compress this protective bubble, potentially shrinking it to within the orbit of Jupiter. With our shield reduced, the Earth would become far more exposed to high-energy radiation from deep space. The increased cosmic ray flux could have two significant consequences. First, by influencing atmospheric chemistry, it might encourage the formation of low-level clouds, potentially leading to a gradual global cooling that alters climate patterns for centuries. Second, the heightened radiation reaching the surface could increase the rate of genetic variation in living organisms, acting as a slow background force for evolutionary change over many generations. This is not a sudden event, but a gradual environmental shift written in the slow rhythm of our galactic orbit. The interaction is a two-way street, as the sun's own motion through the cloud would send waves through the nebula, compressing pockets of gas and dust just enough to trigger the gravitational collapse that births new stars. Our passage would thus leave a legacy of stellar ignition in our wake. How does the knowledge that our planetary climate and the very pace of evolution are periodically influenced by these vast, impersonal clouds reshape our understanding of Earth's story? It binds the biological narrative of our world directly to the structure of the galaxy itself, revealing that our local environment is continuously shaped by the grand architecture of the cosmos. A star is flung from the heart of the galaxy, a celestial traveler set on a one-way journey into the vast unknown. These are hypervelocity stars, and their incredible speed, over 1 million miles per hour, is a direct signature of a gravitational encounter with the supermassive black hole at our galactic center. Their discovery often begins with a subtle anomaly in sky surveys, a star whose motion is radically different from the orderly rotation of the Milky Way's disk. Precise measurements of its trajectory and the Doppler shift of its light confirm its extraordinary velocity, a speed surpassing the galaxy's own escape threshold. The most likely mechanism for this stellar launch involves a binary star system, two stars orbiting one another, that ventures too close to the central black hole. The immense tidal gravity of the black hole can separate the binary pair, capturing one star into a close orbit while sending its companion away at a phenomenal speed. This process, known as the Hill's mechanism, transforms a stellar partnership into a dramatic parting, with one partner held by gravity and the other set free on an endless voyage. Each of these high-speed travelers becomes a unique probe, its trajectory shaped by the total gravitational field it has experienced. By tracing the path of a hypervelocity star backward, astronomers can map the distribution of mass throughout the galaxy, including the vast, invisible halo of dark matter that guides its flight. How does the journey of a single, outgoing star illuminate the hidden architecture of our entire galaxy? These stellar voyages are more than just cosmic curiosities. They are dynamic messengers from the most extreme gravitational environment we know, their silent, high-speed journeys charting the unseen contours of the cosmos itself. A silent, dark nebula drifts for eons, a cosmic cloud so dense it blocks the light of stars behind it. Within this cold expanse of gas and dust, a subtle shift begins. Perhaps a shock wave from a distant supernova ripples through the void, or the cloud's own gravity finally overcomes its internal pressure. A single pocket of the nebula starts to collapse, a fragment pulling itself inward. This is the first quiet step in the birth of a star. As the cloud fragment contracts, its core begins to heat from the immense pressure, growing hotter and denser until the conditions are just right for the miracle of nuclear fusion to ignite. Hydrogen atoms are forced together, forging helium and releasing a torrent of energy. A new protostar flares to life, its light pushing back against the darkness that nurtured it. This newborn star does not simply shine, it actively sculpts its surroundings. Powerful stellar winds and radiation blow away the remaining cocoon of gas, clearing a space around the young sun. Not all the material is expelled, however. A flattened, spinning disk of leftover gas and dust remains in orbit, a celestial construction zone where particles collide and stick together, slowly building up into planets, asteroids, and comets. This is how our own solar system began, from a similar disk that formed around our infant sun over 4.5 billion years ago. Telescopes that see in infrared and radio light, like the James Webb Space Telescope, peer into stellar nurseries such as the Orion Nebula, watching this very process unfold in real time. They reveal the glowing pillars of gas and the dark, dusty disks where new worlds are likely taking shape. What specific combination of density, temperature, and trigger is required to turn a cold cloud into a brilliant engine? This creative event is a cornerstone of galactic evolution, a continuous cycle where the material from earlier generations of stars is gathered and reborn into new suns and new possibilities for planets, perpetually enriching the cosmos with fresh light. The universe's first light holds a subtle but profound secret. The cosmic microwave background is a nearly perfect fossil, a faint afterglow from the Big Bang that fills all of space with a uniform whisper of radiation. This incredible uniformity is a cornerstone of our modern cosmology, suggesting that on the largest scales, the universe looks the same in every direction. But what if that is not entirely true? Precise measurements from space-based observatories like the Planck mission have revealed faint imprints on this ancient light, mysterious anomalies that challenge our most fundamental assumptions. One of the most intriguing is the so-called axis of evil, a surprising alignment of temperature fluctuations that seems to define a preferred direction across the cosmos. This is not a dramatic feature, but a subtle statistical hint, a whisper of a pattern that should not exist according to our standard model. The presence of such a large-scale anisotropy would suggest the universe is not perfectly uniform in all directions. It might carry an imprint of a structure from a time before our universe began, a relic from a more ancient epoch that influenced the birth of our own cosmos. Alternatively, it could point to a universe with a complex, non-trivial topology, a shape that wraps around itself in ways we have not yet imagined, making space itself fundamentally different in one direction compared to another. How would a directional universe change our cosmological models? It would force a profound revision of the cosmological principle, the guiding assumption that there is no special place or direction in the universe. Our entire understanding of cosmic evolution, from the first moments of inflation to the formation of galaxies, is built upon this foundation of uniformity. Finding a confirmed, large-scale directionality would be like discovering that the canvas of the universe has a subtle grain, a fundamental texture that has been guiding the arrangement of everything we see. This would not just be a new piece of data, it would be a call for a new kind of physics, a theory that can explain why the cosmos has a hidden compass. The search for the meaning behind these cosmic whispers continues, turning the oldest light we can see into a map of the deepest questions we can ask. A single magnetic charge drifting through space since the dawn of time could hold the key to rewriting the laws of physics. This 20-second cosmic event revolves around the hypothetical transformation of a magnetic monopole, a particle that possesses just one magnetic pole, either a north or a south, but never both. Our everyday experience with magnets shows they always come with two inseparable poles, but many grand unified theories, which attempt to merge the electromagnetic, weak and strong nuclear forces, insist such solitary poles must exist. If they do, they would be incredibly massive, stable relics from the universe's first moments, and their eventual transition would be a spectacle of change. The process would not be a quiet fade. The immense energy stored within the monopole structure would be released in a sudden burst, potentially triggering a cascade of other rare events. Most dramatically, this energy release could catalyze the transformation of a proton, one of the fundamental, stable building blocks of all visible matter. Imagine a single, ancient particle initiating a chain reaction that reshapes the very stuff of atoms. The search for these elusive entities is a relentless pursuit in physics, with dedicated experiments scanning particle accelerators and ancient minerals for a trace, or monitoring vast volumes of water and ice for the unique signature of a proton's spontaneous change, which could point back to a monopole's influence. How would the sudden, confirmed detection of a magnetic monopole reshape our entire standard model of particle physics? It would be an instant revolution, providing direct evidence for physical theories that reach far beyond our current understanding and offering a tangible link to the universe's condition when all fundamental forces were one. The transformation of such a particle would be more than an endpoint. It would be a cosmic message from an era of perfect unity, a fleeting glimpse into the deepest symmetries that may still govern our reality. A galactic superwind is the breath of a newborn stellar metropolis, an exhalation so powerful it can shape the destiny of an entire galaxy. These colossal outflows begin in starburst galaxies, regions of space where stars are being born at a remarkable rate, hundreds or even thousands of times faster than in our own quiet Milky Way. Within these cosmic nurseries, the most massive stars live fast and conclude their brilliant lives in rapid succession. Each stellar event sends a powerful wave through the surrounding gas, while intense radiation and strong stellar winds from the brilliant, young stars add to the growing pressure. This collective energy does not simply fade away. It merges into a single, coherent river of superheated gas that flows from the galactic disk, moving outwards in opposite directions at millions of miles per hour. This is the galactic superwind, a vast movement of matter and energy on an almost unimaginable scale. We can observe these spectacular events in distant galaxies, their outflows glowing in X-rays from the incredibly hot gas and invisible light from excited elements. The wind acts as a vast recycling system, carrying heavy elements like oxygen, carbon, and iron forged in stellar cores and stellar explosions, launching them far out into the intergalactic void. This process enriches the space between galaxies with the very materials needed for future planets and life, seeding the cosmos for eons to come. Yet this creative force is also an instrument of balance. By moving a galaxy's reservoir of cold gas, the very raw material needed to form new stars, the superwind gently limits the galaxy's future fuel supply. It quiets the era of rapid star formation, putting a natural ceiling on the galaxy's growth and ultimately influencing whether it remains a vibrant spiral or settles into a more tranquil form. How do these immense outflows contribute to the delicate cycles that guide a galaxy's life story? They are a primary regulator, a self-imposed check that prevents a galaxy from using all its resources too quickly. The wind's influence does not stop at the galactic edge. Its energy and momentum press into the surrounding circumgalactic medium, the galaxy's extended atmosphere. In a beautiful paradox, this expansive pressure can sometimes encourage nearby clouds of pristine hydrogen gas, inspiring a new, secondary wave of star formation on the galaxy's outskirts, a final flourish of creativity sparked by the very event that is calming the core. This grand-scale gas dynamics event demonstrates that a galaxy is not an isolated island, but an open system, its internal transformations forever linked to the vast ecosystem of intergalactic space. A star's final journey brings it too close to a sleeping giant. The immense gravity of a black hole does not pull evenly, and the difference in force between the star's near side and its far side overwhelms its own self-gravity. This tidal force stretches the star horizontally while compressing it vertically, pulling it into a thin, long stream of gas in a process aptly named spaghettification. The star is not swallowed whole but transformed in a brilliant, spectacular display. This is a tidal disruption event, a cosmic flare that illuminates the darkness around an otherwise invisible black hole. For a brief period, the accumulation of this stellar material can produce a flare of radiation so intense it outshines every star in its host galaxy combined. This light is not a single color. It erupts across the entire electromagnetic spectrum, from X-rays to radio waves, offering astronomers a multifaceted view of the entire accretion process. The frequency of these events is a direct reflection of the black hole's environment, happening more often in galaxies where stars are densely packed near the central core, and where the black hole itself is not so massive that it consumes stars without the dramatic initial transformation. In some remarkable cases, when the black hole is spinning rapidly, the incoming material can be channeled into powerful, narrow beams shot out from its poles at nearly the speed of light. These relativistic jets turn a brilliant flare into a cosmic lighthouse, signaling the event across vast intergalactic distances. What story is written in the fading light of such a flare? The way the brightness rises and falls over time, the light curve, holds vital clues. It reveals the black hole's mass, the type of star that was transformed, and the intricate dynamics of how gas settles into an accretion disk before crossing the event horizon. This profound transition for a star is, for science, a rare and precious opportunity. It provides a window into the nature of dormant black holes, those quiet giants that typically give no sign of their presence, allowing us to study the fundamental physics of gravity and accretion in one of the most extreme environments the universe can provide. The faintest whisper in the cosmos carries the story of its birth. This final cosmic event takes us back to the very beginning, to a fraction of a second after the Big Bang, when the universe is thought to have undergone a brief, staggering growth spurt known as inflation. This rapid expansion would have shaken the fabric of spacetime itself, generating ripples known as primordial gravitational waves. Unlike the waves from black hole mergers we detect today, these are ancient echoes from the universe's first moments, a fundamental vibration imprinted on everything that followed. Their discovery would be like finding the original signature on the cosmic birth certificate. The most promising place to look for this signature is not in empty space, but in the oldest light we can see, the cosmic microwave background. As this primordial light traveled through the infant universe, the shaking of spacetime would have subtly twisted its polarization, leaving a unique, swirling pattern known as B-modes. Finding this specific fingerprint in the CMB is one of the most important quests in modern cosmology. Sophisticated experiments stationed in some of the most remote and pristine environments on Earth, like the high Antarctic plateau, are tirelessly scanning the sky for this signal. The BICEP array and the next-generation Simons Observatory use incredibly sensitive detectors to parse the faint microwave glow, searching for that telltale swirl in the polarization that could be the mark of inflation. A confirmed detection would do more than just confirm a theory. It would open a direct window into an era of the universe previously inaccessible to science. The strength of the B-mode signal would tell us the energy scale at which inflation occurred, revealing the specific conditions of that expansive growth. This, in turn, would provide crucial clues about how gravity behaves at those incredible energies, offering a rare experimental foothold for theories of quantum gravity. How would knowing the precise tremor of creation reshape our understanding of reality itself? It would connect the largest scales of the cosmos directly to the smallest rules of quantum physics, bridging the universe's dramatic beginning with the physical laws we observe today. This ultimate cosmic ripple represents a final, profound transformation in our journey, turning the entire universe into a laboratory for understanding its own origin. From the quiet fade of heat death to the explosive brilliance of stellar mergers, each cosmic event weaves a thread into the same grand story. This narrative of transformation, spanning from our own solar system to the edge of observable reality, does more than chart the future of matter and energy. It fundamentally reshapes our perception of humanity's brief, brilliant moment within this immense timeline. These 25 possibilities, whether they unfold tomorrow or in a trillion years, challenge us to expand our thinking beyond quarterly reports and generational cycles, urging us to consider the legacy of intelligence itself across cosmic eras. The very act of studying these phenomena pushes the boundaries of human capability, fostering unprecedented international cooperation. Global endeavors like the Event Horizon Telescope, which united observatories across the planet to capture the first image of a black hole, and the LIGO-Virgo collaboration, which listens for the faintest ripples in spacetime, demonstrate how the quest to understand the universe can unite us in shared purpose. This journey inspires a profound duality, a blend of humility and intense curiosity. We are humbled by the realization that our world is a fragile, pale blue dot adrift in a cosmos of unimaginable forces, yet we are driven by an insatiable need to explore, to learn, and to find our meaning within the vastness. How might this cosmic perspective influence our societal ambitions and ethical choices? Knowing that our local environment is subject to change from interstellar clouds, or that our star has a finite lifespan, could inspire a greater urgency in becoming a multi-planet species, or in developing technologies that safeguard civilization from planetary-scale challenges. The study of cosmic evolution offers more than just a forecast of the universe's physical future. It provides a framework for contemplating the long-term trajectory of life, consciousness, and the enduring quest for understanding. This broader view ties every stellar ignition and galactic collision into a single, cohesive human story, one of exploration, resilience, and the endless pursuit of light in the darkness. Our journey through these 25 cosmic possibilities reveals a universe in constant motion, where the gentle drift of galaxies and the sudden flash of a star's final moments are all part of a single, interconnected story of transformation. This grand narrative shows us that creation and change are two sides of the same cosmic process, a cycle where the close of one star's journey provides the materials for new worlds and perhaps new life. The key realization is that our cosmos is not a static museum piece but a living, breathing entity, and our understanding of it must remain as dynamic as the events that shape it. Each new observation, from a gravitational wave signal to the subtle whisper of the cosmic microwave background, can rewrite our textbooks overnight. This ongoing quest for knowledge invites all of us to gaze at the night sky with fresh eyes, to see not just points of light, but the brilliant, chaotic, and beautiful processes unfolding across the vastness. It is a story that belongs to everyone, and its next chapters depend on our continued curiosity and our support for the explorers who build the telescopes and craft the theories. The future of the cosmos is a tale still being written, and we have the extraordinary opportunity to be among its first readers.